Allô. 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 Ah. Test. Test.
Essai, essai.
Ouais. Cet après-midi c'est libre ici, il faut faire on va faire genre les fiches pour savoir il y a des numéros sur ça. Ouais, 4. Sur la liste en fait. Pour sache qui correspond à quoi, tu vois. Ouais. Et pourquoi le VGA il marche pas? Il faudra demander à Louis qu'il fasse un essai.
Marche pas quoi?
Le VGA il marche pas? Si tu branches le VGA.
Ah ouais, c'est vrai, ouais.
Ah non. Non, il n'y a que cet après-midi où c'est libre. Qui viennent cet après-midi. Cet après-midi, après manger direct ici, tester tout. Et au fond, tester le.
Demain t'es à Bruxelles? Samedi, vendredi, samedi?
Ouais, je crois que j'ai pas regardé, mais.
On a un adaptateur VGA HDMI.
Ça fait mal, c'est le nerf. Attends, faut que je prenne 2 piles ici. Attends. Je vais remonter en long. Ah, il est plus tassant, quand même.
Ouais.
De
Non.
toute façon, les piles, je prends comme des piles, on les utilisera quasiment plus, les piles standards. Ah, si, il y en a toujours à Berlin, à Londres.
Ouais, non, mais pas dans cette.
Pas dans le ciel. Bah, si, il faut regarder un ou deux.
Eh, ils sont venus, hier? Je sais pas, 50 fois.
Les numéros, ah non, c'est nous, je crois, parce que j'ai vu là-bas. Ah ouais? Ils sont venus, mais j'ai pas vu.
You can try it if you want. For screen display, it's Control L.
Control.
Good.
Yes.
And there is an on-off button on the left.
Mm.
You need to.
Yes.
Okay.
Nice.
Cool.
Thank you.
No problem. first or the second session?
First one.
Oh, sorry, I put my stuff in the 9-second section.
Okay. So let me first copy his. So which
It's
one?
FSC
That one?
presentation. From can see that glasses.
So I put it under session 10.
Mm-hmm.
Okay.
Oh,
if
yeah,
if you want to put it on display screen, it's Control L,
Mm-hmm.
and then you have this. There is an on/off button in case it's not on. So you just put it like this, and then you can just go like this, and you have this red stuff, which is.
Okay. I try to do that at least.
Yeah.
So, thanks. So you are Nico, Stan, Same wife. So I move your slide. Thank you. So you will keep
I need a PowerPoint.
Yeah.
PPT. You will use PPT or PDF?
I will use the PPT, but later you need to upload it, right?
Okay.
So I want you to upload it.
How can I do this? Okay. Yes.
Can you refrain from uploading my slides for you?
Oh, it's already online.
Okay.
I can remove them. It's okay.
Okay. Then you will get.
Yes. Okay. It's okay.
So is she the next speaker?
I think so. Yeah. Stop. Stop.
Stop.
Yes. I think so. You can confirm it.
Very
right?
confirm. first talk?
Matthias. Yes.
Who's going to give the talk?
I think it's Matthias.
Matthias?
Oh, the name are swapped.
Yeah, it's
It's weird. Okay.
Okay.
Why not? But I'm not sure. I think.
So you know the guy?
No, but he was
No?
there
Okay.
earlier.
Okay.
No, I don't know. I will just try to load the. So you have all the 3 talks here? It's okay? 1, 2, 3. Okay. The first one is this one.
So you think this PP?
Yeah. So just. Oh, it's not. Yeah, but this is strange now. Maybe.
Oh, this is a presentation mode.
Ah, so it's. Do you think that's what she wants?
Don't know, but if you put some comments here, you can
Okay.
actually see it just for yourself.
Ok, so let's.
Okay.
C'est bon? Ça marche pas? Ça marche pas?
Non. C'était où les préférences aussi
C'est pas le
Ouais,
truc qui est en bas,
ouais, je crois.
Ça veut dire qu'on va pouvoir toucher les trucs.
Ouais. Ouais, sur la carte graphique, ouais. Je vais voir.
Je relance? Ouais, mais je suis pas en plein écran là. Non? Y'a pas?
Ça marchait. En fait, c'est pour vous passer en plein
Ouais,
écran.
c'est ça, ouais.
Mais ça fait sauter le projecteur aussi, mais lui, vous le remontez, je sais pas
Ouais.
comment, et ça marche.
Ouais.
Et moi, faut faire je sais pas, ça fait sauter un peu. Ou sinon, c'est que peut-être on est tout de suite en plein écran dès maintenant.
Ouais.
Et on fait la.
Ouais, j'ai essayé, mais ça marche pas en fait.
Ça marche pas.
Je peux pas le faire. Bah. Tant pis, vous avez pas les slides et.
Ouais, ou sinon on peut pas faire un export PDF là.
Bah, elle l'a fait, mais je pense qu'elle veut utiliser le. Je lui ai demandé.
Ouais.
hash you seen. Oh, sorry, you don't speak Hebrew. What is it that you
Duplicate.
duplicate the screen?
It's yeah, I think.
It's
No.
not open.
No, sorry.
It's
No. With the with,
F7 maybe.
yeah, one of those, but F7. Yes, exactly. They changed the symbol. No, it's not a PowerPoint thing. It's something with. You know what? Never mind. I don't want to break anything.
Yeah. I don't know. Okay, we'll just go like this.
Okay. I'm fine with this. Okay. Thank you. It's okay.
You can use this,
Okay.
and it should work. Yeah.
Thank you.
Someone gave me this, it was in the room, so maybe just before the presentation of the speaker, we can make an announcement. I think you'll find something. Thank you very much.
Hi everyone. Good morning. So before the session starts, I have an announcement. Someone found this USB stick. If it's yours, please come to me. The red one. Cryptanalysis. Cryptanalysis of DES with less than 2 to the power of 42 complexity, co-authored by Ali Bihan and Stap and Stap will give the talk.
Thank you for
For example, the best linear approximation of S5 approximates the second bit of input to the XOR of the 4 output bits. The probability of this linear approximation is 12 divided by 64. As in 12 cases of the 64 possible inputs, the parity of this bit is 0, while in 52, the parity is 1. Linear cryptanalysis uses statistical approximations that approximate parity of subsets of bits of the plaintext, ciphertext, and the subkeys. In an ideal cipher, any linear equation involving plaintext bits, ciphertext bits, and key bits would hold with probability close to half when we're considering all the plaintext in the plaintext space and their corresponding ciphertext. Linear cryptanalysis take advantage of the fact that some linear approximations have probabilities different than half. Each approximation has a probability to hold, which is the fraction of plaintext whose encryption satisfies the approximation. The ability to distinguish whether an approximation holds highly depends on the distance of the probability from half. We call this distance the bias of the approximation. A linear approximation is a tuple lambda p, lambda c, and lambda k, where lambda p is subsets of bits of the plaintext, lambda c is a subset of bits of the ciphertext, and lambda k is a subset of bits of the key. The probability of the approximation is the probability that the parity of these subsets of bits is equal to 0. The bias of the approximation is equal to the probability minus half. We are usually interested in approximation with the highest absolute value of the bias. Algorithm 1 finds the parity bits of the key involving the approximation. Given that the approximation holds with probability half plus epsilon, and n plaintext and their corresponding ciphertext, the algorithm counts the number m of plaintext satisfying p lambda p XOR c lambda c equal to 0. The algorithm guesses the parity of the key bits involving the approximation. For example, if epsilon is greater than 0 and m is greater than n half, the algorithm guesses that the parity of the key bits is 0. This algorithm finds only one parity bit of the key. The success rate of the algorithm grows as the absolute value of the bias increases. In particular, the amount of plaintext required for this attack is proportional to 1 over the bias squared. In order to attack the full 16 round test, Matsu uses the best 14 round approximation, as we can see in this slide. Matsu uses algorithm 2 to find the parity bits of the key involving the approximation, same as in algorithm 1, as well as bits of the first and last subkeys. The attack required about 2 to 43 non-plaintext and also time of analysis. We develop an extension of linear cryptanalysis that conditions linear approximations on other linear approximations. We use conditions to discard some of the data, so the bias of the remaining data increase or decrease. As the number of required known plaintext is proportional to 1 over the bias squared, discarding some of the data may improve the number of needed known plaintext. Conditions can be defined by any observable information: plaintext bits, ciphertext bits, and a formula on them. In the case of facial ciphers, we found a specific type of conditions that is highly based on their specific structure. In particular, we refer to bits that are the XOR of the outputs of the F function of the odd rounds, which are computable from the plaintext and the ciphertext. In this example, we can see that PL, the left half of the plaintext, XOR Y1, the output of the F function in the first round, XOR Y3, the output of the F function in the third round, is equal to CR, the left half of the ciphertext. Therefore, we can calculate the output, the XOR of the output of the F function in all the odd rounds from the left half of the plaintext and the right half of the ciphertext. It is important to emphasize that this information on the XOR values is not probabilistic, unlike the situation in a general linear approximation. Such XOR bits, when viewed as linear approximations, typically have bias 0, but they are very useful as conditions to other approximations. I start with an example of such a linear dependency with a single active S-box. As mentioned earlier, this is the best non-trivial linear approximation, and the bias of this linear approximation is 12 divided by 64. In the case of single round, we can compute the output of the f function from the plaintext and the ciphertext. The output of the f function is equal to the left half of the plaintext XOR the left half of the ciphertext. In this table, we calculated the bias of the linear approximation conditioning on all the 4 output bits of S5. It is an important and unexpected observation that only one of the 12 parity 0 cases satisfies LSB equal 1. These are the rate cases in this table, while the other 11 satisfy LSB equal 0. The bias of the approximation without any condition is minus 20 divided by 64. In 12 cases, the parity is 0, and in 52, the parity is 1. When conditioning on LSB equals 0, in 11 cases, the parity is 0, and in 21, the parity is 1. And when we're conditioning on LSB equal 1, the red case, in 1 case, the parity is 0, and in 31, the parity is 1. So consider only encryptions in which the LSB is 1. In this half of the data, the bias grows from minus 20 divided by 64 to minus 30 divided by 64, while the bias of the rest of the data reduces to minus 10 divided by 64. We will exemplify this with a scan from Adi Shamir's crypto paper. On the left side of the vertical line appear all the outputs with their second bit of input is 0. And on the right side of the line, all the outputs with their second bit of input is 1. Shamir circled the values with an even parity of the 4 output bits. Therefore, in the left side, he circled the outputs which satisfy the parity approximation, and in the right side, he circled the outputs which do not satisfy the parity approximation. The blue cases are the cases that satisfy the approximation, and we can see that only one of the blue cases is odd. Therefore, we see that when we condition on the odd cases in which LSB equal to 1, we get 1 value against 31. It's not only that we can do it for a single round, we can extend conditional approximations to more than 1 round. In this case, we show it on 4. So consider 4 successive rounds taken from Matsui as best linear approximation. This approximation uses 3 active S boxes, S5 on the first and third round, and S1 on the fourth round. Notice that both odd rounds have the same active S box, and that we can calculate the XOR of the outputs of S5 in all the odd rounds from the plaintext and the ciphertext. So what we are going to do is we are going to condition the bias of the linear approximation on these XOR values. In this table, we calculated the bias of the linear approximation conditioning on all the 4 XOR output bits of S5. We can see that in the case that the XOR of the LSB of the output of S5 is equal to 1, the bias of the linear approximation is 0. These are the red cases in the table. So using only the plaintext in which the XOR of the LSB is equal to 0, increase the bias by a factor of 2. So we need a quarter of the data compared to the regular linear attack with the same approximation, but this is the amount of data that remain after we discard half. So in total, we need half of the original data. We discard the plaintext in which the XOR of the LSB is equal to 1, and then we get the required quarter. The same factor of saving holds for an 8-round reduced death. The same factor of saving holds for a 12-round reduced death, and the same factor of saving holds for the full 16-round death, but this is not the best attack on the full death. As mentioned earlier, in order to attack the full 16-round death, Matsui uses the best 14-round approximation, denoted here by lambda 1. In this approximation, S5 is active in all the odd rounds, so we can do here the same. In this table, we calculated the bias of lambda 1, conditioning on all the 4 XOR output bits of S5. The bias of lambda 1, when conditioned on LSB equal 1, the red cases in the table, is improved by a small factor. So using this conditional linear approximation, we can save 12% over Matsui's attack. But we want to save more. So our attack is based on two 14-round linear approximations. Lambda 1 is the best 14-round linear approximation, same as Matsu uses. And lambda 2 differs from lambda 1 in the first round. Notice that S5 is active in all the odd rounds in both linear approximations. In these tables, we calculated the bias of lambda 1 and lambda 2, conditioning on all the 4 XOR output bits of S5. In the case of lambda 1, the average bias of the red entries with XOR LSB equal to 1 is greater than the average bias of the entries with XOR LSB equal to 0. In the case of lambda 2, the average bias of the red entries with XOR LSB equal to 0 is greater than the average bias of the entries with XOR LSB equal to 1. So the bias of lambda 1, when conditioned on LSB equal to 1, is improved by a factor of 2 to the 0.6. The bias of lambda 2, which was much worse than the bias of lambda 1, is improved by a higher factor of 2 to the 0.8. So the biases are almost similar after the improvement. In practice, in our attack, we use these two conditional linear approximations in a complex way. So in total, we can improve the complexity of the attack by a factor of about 2. We tested most techniques with our test programs, and we can see in these graphs all the attacks against the data encryption standard. This is the success rate of the attack, and this is the complexity of the attack. I mean, the maximum between the number of needed plaintext and the time of analysis. The brown curve is differential cryptanalysis. The orange one is linear cryptanalysis, and the red one is conditional linear cryptanalysis. Between the orange and the red curve, we can see extensions of linear cryptanalysis. To summarize, in this talk, we showed that linear approximations are highly affected by conditioning them on other approximations. We showed how to use such conditional approximations for attacks, leading to the best current attack against the data encryption standard. The simplest case is conditioning linear approximations on the XOR of the output of the F function in all the odd rounds. We showed that even using a single conditional linear approximation, we can save 12% over Matsui's attack. Using both conditional linear approximations lead to attack against DES with complexity less than 2 to 42. Thank you.
Any question for staff?
Thank you for the talk. So I just wonder if your method can be applied to other ciphers than this. So,
Okay,
for
this
example,
technique can...
SPN ciphers in?
Okay, in the case of SPN ciphers, we can condition linear approximations on any other linear approximations, and we can gain improving the bias in some cases. Okay? Any kind of linear approximation.
More question? Actually, I have one. Yeah. So, did you try to do an experimental verification of your attack?
Of course. The graph we saw was experimentally tried.
Oh, that's real data?
Yes.
Okay, thank you. More question? If no, let's thank staff again.
Thank you.
So,
Sorry about this.
Okay, so the second talk is entitled Separable Statistics and Multidimensional Linear Cryptanalysis, joined between Stan Fauskager and Igor Samaf, and Igor will give us the talk.
Okay, thank you for presentation. So I'm quite grateful to the previous speaker for introducing linear cryptanalysis and D-structure. So Matsui linear cryptanalysis is based on distribution of XOR of plain text bits X1, XS, and ciphertext bits Y1, YT in algorithm 1. In algorithm 2, bits X are input to the second round of the encryption, and Y inputs to the last round of the encryption. So we managed to find a method to compute the joint distribution of X and Y that is a vectorial random variable. And this was the starting point in our work. Both distributions, Matsui's distribution and our distribution, are approximations. And they depend on the small sets of cipher key bits or linear combination of the cipher key bits. And then briefly, algorithm 2 cryptanalysis is applied. This is outline of the rest of the talk. So first, I remind about Matsui algorithm 2 and about logarithmic likelihood ratio statistic. Then I introduce a new statistic, which is more suitable for multidimensional cryptanalysis. And then show that deciding on values of the key bits relevant to the statistic may be represented as an instance of optimization problem. And I will introduce a search algorithm to solve this problem. And then give some details on implementation of the attack against the 16-round DS. And then show how we managed to compute multidimensional distribution in Feistel ciphers. And then I will go to conclusions. Okay, first is about Matsui algorithm 2 and conventional statistic. In algorithm 2 by Matsui, encryption is split into 3 parts. It's the first round of the encryption, internal rounds, and the last one. And our vector is X and Y. And its distribution depends somehow on some key bits which are relevant to the internal rounds. But observation is not available because observation depends not only on the plain text, but also on some key bits from the first round. And the same for observation Y. So one can say that distribution on X and Y and observation depend on all these key bits shown here. Now, logarithmic likelihood ratio statistic is used to distinguish two distributions with densities, distribution P and Q, by observing independent observations. This is the most powerful test according to Neyman-Pearson lemma. And the test says that we accept P if the value of this function, which is sum of logarithms of values, ratio of values P under observation and Q, is larger than some threshold. And left-hand side function is called logarithmic likelihood ratio statistic. It's already shown that, I'm sorry, it's too fast. As already mentioned, distribution of X and Y depends on some key bits, and the observation of X and Y depends on some other key bits. So LRR statistic should depend on all these key bits. And this statistic may be used to distinguish correct value of relevant key bits against incorrect value. However, to do that, we need so many computations of values of the statistic. So it's feasible when the size of the set is relatively small. But when vector x and y is large, its distribution observation depends on so many qubits, and this is not efficient. So instead, in this work, we suggest using a new statistic, and with the new statistic, computation is much faster. In our experimenting with DS, it's 1,000 times faster than with conventional LRR statistic. And this new statistic reflects the structure of the round function. It depends on how S boxes, how rounds implement using S boxes. And of course, our new statistic is not optimal because LRR statistic is optimal according to Neyman-Pearson lemma. But this statistic is not optimal. But as we can compute, we solve statistical problem much faster. Trade-off is positive. So now I explain how this new statistic was constructed. We have our vector x and y, and we know its distribution. And we take some subvectors of this vector. We take m subvectors. Or I call this subvectors projections. It may be any functions in these bits. And those projections are taking such that distribution observation for each of them depend on a low number of key bits. So this is key bits which are relevant to distribution of this, and these are key bits which are relevant to observation of this. Now we construct LRR statistic for each of these subvectors, and then consider vector of these LRR statistics. As we know distribution of this vector, it's easy to compute distribution of this vector, and easy to compute distribution of this vector. And asymptotically, this vector is distributed as an m-varied normal random variable. If a key is correct, so we have one distribution. If key is incorrect, so distribution is close to something opposite. And these are parameters of the distribution, some mean vector mu, a covariance matrix C, and the number of plaintext n. Now the problem is to distinguish these two normal distributions. We can use again LRR statistic to do that. Usually when you want to distinguish two multivariate normal distributions, LRR statistic is quadratic. But in this case, because covariance matrix is the same, statistic degenerates to linear. So that this statistic to distinguish these two is the sum of the statistics for each of the projections. So that one can say that this statistic is separable. So that statistic represented the sum of statistics with for smaller parameters. Such statistics were called separable, and the theory of such statistics was developed by Russian mathematicians Ivchenko and Medvedev quite long ago. But we use here only notion of the statistic and not any theory about them. Now, because we know distribution of everything, we can compute distribution of our main statistic. It's one varied normal distribution with parameters U, it's expectation, and U, it's variance. For some explicit positive U, if key is correct. If it's not correct, it's something opposite. Okay. So now, what we need in cryptanalysis? In cryptanalysis, we need to solve this inequality, so that we need to find values of the key such that this inequality is satisfied. And then we accept this as a correct one. But we want to do that without brute forcing these key bits. And that can be done because our statistic is a sum of some functions in a low number of of variables. And in our experimenting with DES, the size of this set is 54 bits, and the size of this set for every I is around 20. And that can be represented as solving an optimization problem, and method to solve this optimization problem is a tree search. Now I discuss optimization problem and introduce search algorithm. So optimization problem is to find, say in this small example, to find the binary x1, x2, x3 such that this function is larger than 1.3. And functions s1, s2, s3 are real valued functions defined on vectors of length 2. This is the definition of S1, definition of S2, S3. You can check that 1, 1, 1 is the only solution to this problem, because if 1, 1, 1, we can see that 1, 1, 1 chooses this column, and this column, and sum of all three values is 1.4, is bigger than 1.3. So solution is working over search tree. We start at the root, then we assign to x1 value 0 and look at this inequality and try to understand if it's feasible or not. If it's not feasible, we cut this branch. In x1, 0, it's not feasible, and we try x1 and check if it's feasible. It's feasible, then we continue. So want to check 6 linear inequalities in this example, and brute force takes 8 inequalities. So this is faster. In the same way, we solve what we need, actually, this inequality. Now, output of this research is key candidates for the final brute force. And as distribution of the main statistic is known, we can compute theoretically success probability of this attack and the number of wrong solutions that is a key candidate to brute force. That is done theoretically. Now I say a few words about implementation details for DES. So DES input to DES is a 64-bit block. It's split into two parts. It's a 32-bit block, 32-bit blocks. This is plain text. It's a cipher text after 16 rounds. It's a cipher key. Matsui best linear approximation for 14 rounds is given here. It's a sum of 8 bits. Those bits are part of the cipher text. This bit is input to the last round. These 3 bits, sorry. So these 3 bits are input to the second round. We take all these bits, it's a linear combination that is XOR of all these 8 bits, but we take all these 8 bits as a vector and add more bits, and we get a vector, sorry, again. And we get vector of length 14, and by symmetry, and we, so it's very close to these 2 buttons. So we can compute distribution of this vector. It's a vector of length 14. And by DES symmetry, we can use another vector also of length 14. And distributions are the same after permuting the bits. As these 2 vectors incorporate different internal bits of the encryption, we consider them independent. And computing their distribution with our formulas took a few seconds. Now, for each of them, for each of these 2 vectors, we take 14 projections. Overall, 28 projections represented here. And for each projection, LR statistic depends on at most 21 qubits. Overall, the number of qubits involved here is 54. Now we construct two separable statistics and apply search algorithm. And search algorithm reconstructs 54-bit key candidates for the final brute force. So how it looks for one projection is shown here. So we take projection H1, this vector of length 10, and all relevant qubits, those qubits, I remind, qubits which affect distribution of this vector. And those qubits affect observation of this vector. The set incorporates 20 unknowns written here. There's unknowns from the DES master key. And we can compute to power 20 values of the statistic S1. And similar is done for all other 27 projections. So now we want to construct a tree and work over this tree. In this case, we need to order relevant qubits to run this tree search. And the order is very easy. We take the first variable, which appears in the maximum number of these subsets. So the second most common x19, and so on. And the order actually affects complexity of the tree. Now we run experiment. We fix a desirable success rate. It's, for example, 83%. It's close to Matsui, but a little bit different due to some bad planning. Then we solve the equation in n. N is the number of plain text. And another parameter is here is a threshold. We find threshold for our statistics such that the number of plain text equals the number of keys to brute force in the final stage of the analysis. And we got that number of plain text is 2 power 41.8. And then we run a search tree algorithm. This is complexity in log scale. This is number of nodes at each level of the tree. So, and we got finally the number of key candidates in relevant qubits is given by this number. And this is number of keys to brute force is the same as here. As this was done experimentally, that is, this somehow gives idea that our method is correct. But however, the number of nodes in the tree is 2 power 45.5. It is larger than complexity of brute force, but constructing one node is a very simple operation. It's just checking two linear inequalities with low precision real numbers. So in bit operations, constructing so many nodes in the tree is lower than brute forcing with DS so many keys. As it improves Matsui result on DS, which according to the previous talk was 2 power 43, with success rate was 85%. But remark that in contrast with Matsui result, this success rate was computed experimentally for 8 rounds and then extrapolated to 16 rounds. But this success rate is computed purely theoretically. Now I want to say a few words, if I have time, about how to compute multidimensional distributions in phase-tail ciphers. So assume that we have R round DES. This is a plain text, this is ciphertext, this is cipher key. Assume that X is random. So every bit in encryption algorithm is a random variable. And let E be any event inside the encryption. And we want to compute its probability. And I want to formalize this problem to put into mathematical form. So the construction is the following, that x0, x1, xr plus 1, this is internal blocks in DES, randomly independent 32-bit blocks. but it doesn't depend. It doesn't define a cipher. And we take some auxiliary event C, which defines actually the cipher, and that is given by these formulas. And f is a round function of DES, and ki are fixed round keys. Now, a probability of the event is actually probability of the event in this scheme under condition of the C. And by conditional probability formula, we can write this ratio. And then probability of this event is very easy to compute, is 2 power minus this number. So, and we want to find this probability. But as this event depends on all key bits of the cipher, this is actually infeasible to compute. So it's a very complicated function. So we need some approximation to this. And that may be done by relaxing this event C, which defines DES. So we take a large event in the sense that main event C, which defines cipher, implies event C alpha, as it is given by these formulas, where alpha I is a subset of indices for each subblock in DES. And alpha is a concatenation of this, not concatenation, it's a vector of this subsets of indices. And probability of this event, it's also very easy to compute, it's given by this formula. And now, instead of this, we compute its approximation. Why this is approximation? It's because if we extend, take a larger subset of indices, C alpha tends to C. But we accept anyway that it's approximation. And for this conditional probability, we use the same formula. And then we need to compute the probability of our targeted event together with this event. And that was actually done in Matsui work implicitly. But I did it explicitly here. And that is more feasible because this event depends only on a low number of the key bits. Now I should say something about trails. So assume that you want to compute distribution of this vector. These two subvectors are input to encryption function. This is output after R rounds. Those are some indices. We define some event C alpha. Our approximation depends on how we choose this event. Assume that we take some event C alpha, then we construct trail. Trail consists of some input bits for Fi and some output bits of Fi. And we call the trail regular if this condition is satisfied, where Xi gamma input bits relevant to Fi alpha. And this condition is very similar to Matsui's condition. In Matsui condition, if you remember that this beta is XOR of these two. But here we consider not a linear approximation, we consider it's vectorial random variables. In this case, we need a bit different, but the sense is the same. We need some condition on the trail. And for regular trails, which satisfies this condition, we can compute distribution of this vector by using some convolution type formula. This formula is given on this slide. So Z, again, I remind that is a vector distribution of which we want to compute. We want to compute probability that Z equals some vector A. It means that this part equals this part, this part equals this part, this part equals this part, and this part equals this part, and the condition C alpha. And this is exact formula. And this is sum of products of probabilities from round subvector distributions. And they are computed from the definition of DES round. And this has some relevant key bits. And this formula is quite complicated to handle because a lot of summons in this formula. But due to the round structure of the cipher, we can split encryption into 2 parts and compute it by parts. And in this case, it's very easy computation. It's only a few seconds for 14-round DS to compute distribution of very large vector, actually. Okay, almost done with conclusions. So in this work, we suggest method of computing joint distributions of encryption internal bits X and Y for faceted cipher. For SPN, it's about the same logic may be applied. And we realize that conventional logarithmic likelihood ratio statistic is inefficient. So we suggested new statistic which reflects round structure of the round function. We computed its distribution and able to predict success probability and the size of the final brute force. And also efficient search algorithm to find key candidates which fall into critical region is suggested. So we got an improvement of Matsui result in DS, no, at least in bit operations. And we're able to predict correctly success probability. For 8 rounds, we're able to check if our success probability is a real success probability. And the number of final key candidates for 16-round DS. And our search algorithm to solve optimization problem is 1,000 times faster than brute forcing all relevant key bits. This is the end of my talk. Thank you very much.
Question for Igor? I have one. Can you go back to the number of nodes?
Which one?
Yep, here.
Mm-hmm.
So I can see the number of nodes is much higher than the complexity for brute force. And so when you build a tree, do you need to actually sort the nodes? Like, do you need a binary search tree? Or?
This is a binary search tree. We construct nodes, but constructing node is very simple operation. It's only few XORs.
Yeah, but for each insertion, there will be some more operation according to the depth of the tree, right?
No, for each, this is the number of nodes. Oh, I'm sorry. This is the number of nodes. So complexity of the tree is the number of nodes, of course. It's proportional to the number of nodes. But complexity to construct one node is a few XORs.
Yeah, I mean, constructing the entire tree, is it complexity n times log n?
No. Complexity of the tree is the number of nodes. We have some node, and we get some new node. And we should check 2 linear inequalities at this node. If they are satisfied, we continue constructing node. If not satisfied, we cut this branch. So that complexity of this node, to checking 2 linear inequalities with real numbers.
Okay.
Okay.
More question for Igor? If not, let's thank Igor again.
Okay, thank you. I don't know how to go back.
So the last talk of the session is entitled Generating Graphs Packed with Paths. It's joined between Philip Varna and Matthias Hall Anderson, and Matthias will give the talk.
Thank you. Thank you for the introduction. So the talk is divided into 5 sections. So first we're going to have some motivation about what we're trying to do and some of the simple folklore about linear cryptanalysis. Then we're going to rephrase linear cryptanalysis as a set of graph problems, and then we're going to look at some heuristics for finding good subgraphs and why this is of interest for SPNs. And then we're going to look at some plots and results, and then lastly some future work. So first, the motivation. So since the 90s, we have been knowing about linear differential distinguishers. And generally, when you suggest a new design, one of the things that you have to argue about is provide some sort of argument against your resilience to linear and differential cryptanalysis. And of course, what is of interest is to determine the optimal parameters of these distinguishers, as well as the expected power of our distinguishers over the key space. So in this presentation, we'll primarily focus on linear cryptanalysis, both because of the session and also because the differential case is largely analogous for the work presented here. So for an hour-round cipher, iterated cipher, we have this notion of a trail, which defines approximations over every round function. And the idea is that we can calculate the correlation of the approximation over every round function efficiently because it decomposes into relatively small and simple non-linear components for which we can enumerate the full domain. And then we have this notion of a correlation contribution for a trail, which is simply the product of the correlations over the approximations over all the rounds. And then we can describe the correlation for an approximation between alpha and beta over the entire cipher simply as the sum of correlation contributions over all the trails under suitable assumptions. And then for key alternating ciphers, we generally assume that the analysis becomes if you consider the square correlation, then it becomes independent of the key. Essentially, it becomes a sign. And then we have this notion of an ELP, which will be the expected correlation amplitude for our distinguisher, and we can estimate against suitable assumptions this as the sum of the square correlations of trails. And then what happens in practice is that we sum over some smaller subset, calligraphic U. Often this calligraphic U is merely a singleton, in which case you're assuming that there is a single dominant trail. So the idea is that we'll sum over the dominant terms. We will consider the dominant terms of the summation, and they will give us a good estimate for the entire sum. But of course, the performance of a single trail and even any small set of trails is not necessarily a good indication about your design's susceptibility to linear and differential cryptanalysis. And this is the problem that we're trying to mitigate. And current methods for considering multiple trails of a whole are linear in the number of trails. And then for designs which have a very large number of good trails, this is suboptimal. So we would like to get some sublinearity, which is the goal of this work. And to get into this frame of mind, we are going to rephrase linear cryptanalysis as a graph problem. So the graph is going to be what we call a multi-stage graph. So in this case, we have a cipher of 3 rounds. And it's a directed graph here going from left to right, but I omit the arrows. And the vertices are parodies for linear cryptanalysis and similar for differential. And the edges then naturally become the approximations over the round functions. And the length of the edge is the squared correlation of the approximation over the round function between the source and the destination of the edge. Then if we consider, with this notation, then if we consider the length multiplicatively, then paths through the graph becomes trails. And the length of a path becomes the squared correlation contribution of the particular trail. And with this, we define the notion of a weight of the graph between an alpha and a beta as the input and output nodes. And this corresponds to the hull, which is the sum over the lengths of every path between alpha and beta. One observation here is, one very simple observation here is that you can calculate this in linear time over the number of edges, basically using bottom-up memorization. So you start by calculating the Hall between any alpha and any U node, which is trivial in this case. And then we can calculate the Hall between any alpha and any V node by, at any V node, calculating a weighted sum of the Halls between the alpha and the U nodes. And then we progress similarly for the beta nodes, again calculating a weighted sum over the Halls between the alpha nodes and the V nodes. Also note that we can calculate, we get for free the weight between alpha and any beta node. So we don't need to consider any pair. But of course, this is all nice and fine, but the problem here is that the graph is far too large, right? So if we naively define the graph as this, sure, the algorithm runs in linear time, but the graph has exponential size. So what's the use? So the question is, can we find some suitable subgraphs that contain, in a sense, most of the good trails? And of course, the observation here is that we are not looking for good trails necessarily. We're looking at the more general problem of finding these good graphs. I.e., we want the maximization of the weight between any alpha-beta pair to be large. And for this, we have devised some heuristics. And in this case, we're going to be focusing primarily on SPNs, for which we have the best heuristics. So the overall method will be that we'll pick some sort of disjoint families of edges, which we'll describe. Then we'll prune the families using an approximation of the graph defined by these edges. And then finally, we will expand these families to a full graph. And then at the end, we'll do some cleanup work on the graph. Oh, shit. So one immediate and easy observation is that if we have any edge of length 0, we can just remove it. This corresponds to a trail with length 0, and it doesn't contribute to the Hall. And then once we've removed it, we can remove any vertex that doesn't have a predecessor or successor because no path can traverse it. But this still doesn't get us far enough. So now describing these families of edges. So this is probably best described by giving an example. So consider a 16-bit SPN, a small toy cipher, with 4 identical S boxes. Then if where we have the following 2 approximations over the S box with the following squared correlation. So 3 goes to D with correlation 2 to the minus 2, and 7 goes to 4 with the squared correlation 2 to the minus 2. Then if we have the S box pattern, which we call it, this will be a family, one of the families, as 1 to 1.2 to the minus 2, 1.2 to the minus 2. This corresponds to every approximation over the S boxes, which have this particular pattern of squared correlations. So in particular, the first and the third S box must be inactive. And the second and the last S box is basically any combination of the approximations above. Yeah. And then we also naturally have the projection onto the first and the second coordinate, which corresponds to the input pair on the set of all input parities and set of all output parities for the family. Okay. Then if we have some set of families, so we have some set of S-box patterns, then we can consider the graph defined by this set in a natural way by simply just expanding every member of the set. These forms our edges, and then our vertices is just the union of the projections. So suppose we have some set of S-box patterns defining this subgraph that is of our interest. Then we can immediately observe that for any intermediate stage in the graph, so any node that is not an input and an output node, if V does not lie in the set of both, if V does not lie both in the set of input and output parities of the expansion of all families, then it's immediately pruned because it can't have a predecessor or successor. Our problem now is that, so we've defined these families, we can keep the description of the families in memory, but the expansion we cannot possibly keep in memory. So the idea will be that can we somehow prune on these families before expanding them, so that we have less families to expand and we can manage the graph. And the overall approach, and the more details in the paper, is that we generate an approximation of the graph by applying a compression function, very like differential, truncated differentials, in such a way that if there is an edge in the original graph and hence a path between two nodes in the original graph, then there is also an edge in the truncated graph, but not necessarily the converse. And then our algorithm is basically like iteratively refining the compression until you reach the trivial case. So we start by generating some set of patterns using a heuristic. We have a generic heuristic, but if you have some cipher specific knowledge, you could apply this. And then we pick a compression factor. Then we generate this truncated graph by applying the compression on every vertex when we expand the members of the set. And then prune on the truncated graph. Then we remove any family, any S-box set, any S-box pattern for which all members of the expanded S-box pattern are not in the truncated graph, because if a member is not in the truncated graph, it cannot be in the full graph either. The truncated graph is sort of strictly more connected. And then we refine the compression until we get to the trivial case. And then we expand the graph. Okay. Notice here that in a sense this procedure is lossless, right? So you're not removing something that could otherwise have created additional paths. Like once you've fixed your set of patterns, the graph that you will get out in the end will have the same set of paths through the cipher. So suppose we have this following graph at the end, then we observe the problem, and this is basically that if we apply now pruning to the intermediate rounds at the end after expansion, then we will lose a large part of our search space. And the way that we heuristically avoid this for SPNs is that we add some vertices that are not in the set of the expanded families that are optimal for the vertices that would otherwise be pruned. So the input and output vertices, see if we can do this, here and here, here and here, that would otherwise be pruned, then we add optimal input and output vertices to ensure that they're not. Okay, then we can take a look at some plots and results. So we've implemented this heuristic in a publicly available tool that we call cryptograph. And for SPNs, it's very simple to use. It's essentially file and forget. You give it a linear layer, you give it the nonlinear layer, and it can start giving you analysis. So of course, one thing you can do once you've found this cryptograph is that you can plot it at least for small parameters, so that you can actually look at it with your eyes. And we hope that this will be of use to cipher designers who can then visualize how the whole looks. So here's a plot for present. So we immediately see basically the Okuma observation that you have this huge amount of trails because you have this level of freedom in your choice of approximations over the round functions. In contrast, here's a plot for gift, which has this which is essentially a present-like cipher with this specially crafted bogey permutation that is designed to avoid exactly this observation that is found in Okuma, that you have this very large number of Hemingway 1 trails that are all roughly equally good, right? So in particular for present, you cannot really upper bound. You cannot simply upper bound the squared correlation of any particular trail and take that as indicative of your cipher's susceptibility to linear cryptanalysis, because there is this very strong Hall effect. So we've applied the technique to 17 different ciphers for both linear and differential cryptanalysis. And I want to highlight the following results. So we have four present-like designs. And for the present-like designs, we generally find a very, very large number of trails. So just as an extreme example for Puffin, we find actually the hole that we end up considering between our approximations contains 2 to the 112 trails. And then for present-like designs, we generally see about 2 to the 60, right? So for present, we also see 2 to the 60, which is also not feasible to do if you would have to linearly enumerate them in linear time. So we improved the analysis of present by essentially considering a vast number of trails at really no additional time. And then for rectangle, we also improved the hull analysis that is found in that work, in the original design work, by considering a few 100,000 trails. And lastly, some points of future work. So we would like to add support for ARX ciphers. We need some good heuristics for ARX ciphers. The current heuristics obviously don't port. And it's not immediately obvious how to do this. And we would also like to have some better heuristics for faster networks. We do have support for faster networks, but we would like to have some less generic heuristics. Yes, that's the end of my talk.
Question for Matthias?
Thanks for the talk. You said that for the tool you intended to be helpful for designers. So if I am now designing a new SPN cipher, what do I have to do to apply this tool to my new design?
So for SPNs, it's really, really simple. You simply supply the S boxes, so you can have different S boxes in the same round, but we don't currently, only for technical reasons, don't support different S boxes in different rounds. But you give it the S boxes. You give it the linear layer, you implement this in a Rust function, and then even if you also give us the key schedule, we can also generate an approximation of the correlation distribution over the key space, because this method also gives easily rise to a way to quickly enumerate the correlation over the key space. You basically just reweight the graph according to the particular expanded key that you get from running the key schedule. So for SPNs, it's really simple to apply.
Okay, nice, thanks.
For him?
So does your tools also support partial SBox layers like LowMC?
I think we do. I'm not super sure about that actually.
Okay.
Let me see. The question is whether we've added that subsequently to this, because we kept working on the tool.
I also have a question. So
yes.
Maybe I missed that part, but do you have a bound of the results and the actual situation?
Could you rephrase the question?
So do you have a bound between the result you find and the actual situation? Or is there error?
So the results that we find, right? So if you give me these SBox families, then I will consider every trail that lies in this expansion. So if you give me, say, all the Hemingway 1 approximations over all the Hemingway 1 parodies over the SBox, say for present, then I can give you the result for the whole over every trail that lies in this, right? So in a sense, it's more robust. Right?
I see.
So the heuristic step is choosing this calligraphic P set of patterns. I don't know if this is if that answers your question.
Yep.
Okay.
Any more questions? If not, let's thank Matthias and all other speakers in the session. So let me do this again. If this is yours, come to me. Otherwise, I will pass to Jeremy. What is it? USB stick.
Sorry? Okay. Oh, I see.
Yeah, welcome to the last session of FSE. It will be a session about new designs, and there will be 3 talks. The first talk is Adiantum, Length-Preserving Encryption for Entry-Level Processors by Paul Crowley and Eric Biggers, and Paul will give the talk.
Thank you very much for the introduction. I want to talk about a problem. I'm on the Android platform security team, and I want to talk about a problem myself and my colleague Eric faced, and what we did about it. This is going to be one of the less technical talks. You know, it's the last day, we're all tired. But also, Adiantum is not a sort of deep technical advance. It's a combination of well-understood techniques, and what I want to talk about is the practical problem that we faced, and why we chose Adiantum as a way of solving it. So, if any of you who have Android devices in this room, undoubtedly those devices will be encrypted. And those devices will have something like ARM cryptographic extensions, or perhaps even an inline crypto engine that makes AES super fast. And so those devices will be encrypted using AES. But for a lot of devices not in this room, devices being, for example, being used in developing countries, or IoT devices or something like that, they have processors like the Cortex-A7 processor, which lack the AES-CE extensions, and on those devices, AES is just not an acceptable performance. And so this affects storage encryption, which is my area, but it affects all sorts of things like, for example, TLS connections. And in TLS, the solution to this was RFC 7539, which uses Dan Bernstein's primitives, cha-cha, poly1305, to build a fairly straightforward AEAD mode that you can use for these kinds of applications. And it is, I'm afraid I don't have benchmarks, but they're similar to the benchmarks I'll show later for Adiantum. It is way faster than AES on these devices, and that gives users an acceptable performance. And so for an internet connection, for network connections, RFC 7539 solves this problem. Trouble is, because it's an AEAD mode, the ciphertext has to be larger than the plaintext. There has to be room for a MAC, and there has to be a nonce which is not reused. For storage encryption, we have to have a ciphertext which is the same size as the plaintext. And I'll get onto why that is. So you're probably, the most familiar example of storage encryption is the full disk encryption. For every physical sector on the device, we have a virtual sector, and a write to the virtual sector, which has to be exactly 4 kilobytes because that's what the software expects, is encrypted and is sent to the hardware as exactly 4 kilobytes because that's what the hardware supports. If we had flash storage that gave us a little bit more room, we could have a few extra bytes in our sectors, then we could use an AEAD mode, store these extra bytes. That would change the picture there a little bit. I've been saying this since about 2000. I've been having this conversation with, like, if the storage manufacturers could just give us a bit of extra room here, we could really do something different. Even if they were to turn around tomorrow and say, okay, we're going to do it, it would take a long time for that hardware to become available. And to me, this problem is urgent. There are devices out there that are not using encryption because we don't have a solution to this. Now, on a lot of more recent Android devices, we don't use full disk encryption. We use file-based encryption. And at first, I hoped that this would give us another way to address the problem. It would allow us to that the file-based encryption could mean we could have a bit more flexibility in our format, and maybe we could make room for a little bit of extra storage for a nonce and a Mac. Sadly, it doesn't really work that way. First of all, that would be a major engineering effort by itself. To write a file system that could make room for this, it would be a pretty deep change. But even given those deep changes, there would be certain circumstances where you would see a major hit. So databases, for example, they expect that if they have a multi-gigabyte database file, they can go to some 4 kilobyte line sector, make a change, and see a single write. If we have to update a nonce and a Mac for that sector, making it a little bit larger, that means it's got to be at least 2 writes, and when they read from it, at least 2 reads. That halves the speed. It breaks atomicity, makes it it's a major challenge to update this in a way that is atomic. But worse than that, it's really bad for the flash devices. The lifetime of a flash device is measured in writes. If under these circumstances we're doubling the number of writes, it will halve the lifetime of the flash device, which would be a serious inconvenience for users. So even in the file-based encryption scenario, we can't get away from this problem that we have to have the ciphertext the same size as the plaintext. In order to call itself an Android device, a device has to pass what we call the compatibility definition document. And for many years now, the CDD has required that Android devices be encrypted. But there's a carve-out. And there's a carve-out so that people in developing world countries can have a full-fledged smartphone operating system on the hardware that people there can afford. That carve-out says that if you encrypt AES at below 50 megabytes a second, you may ship an unencrypted device. Now, that's sad in that lots of people have unencrypted devices, but it also provides some pretty weird incentives. If you can just slow down AES in your device to 49 megabytes a second, bingo, you can ship that device unencrypted, and now your device is faster than the device that runs at 51 megabytes a second, which is unencrypted. So I was pretty unsatisfied with this, and I wanted to fix it. So here's what we did. So given that the ciphertext has to be the same size as the plaintext, we can't achieve the formal properties of an AEAD mode. It has to be deterministic because it's a bijection. We rewrite new content to old sectors, so there's no way to store a nonce that isn't reused. And the best we can achieve is a tweakable super pseudo-random permutation. We want, for every sector, we want there to be a bijection between the plaintext and the ciphertext, which is indistinguishable from a random permutation. And for all of those sectors, we want it to be a family of permutations that's indistinguishable from a family of random permutations. And that's assuming the attacker has access to the encryption and decryption functions. So an example of a tweakable super pseudo-random permutation is AES XTS, and this is what we use on modern file-based encrypted devices. To encrypt a 4 kilobyte sector, we simply apply AES XTS 256 times in parallel units. And so the tweak comes in 2 parts. There's a part for the offset into the sector, and there's a part within the sector for the offset within the sector. However, on the devices we target, we see performance of around 59 cycles per byte, which is like 20 megasecond, which is way too slow for our users' experience. If they're loading an app or something, it takes really visibly too long, and so we can't expect that. Our users won't accept it. We can achieve a better security guarantee if our super pseudo-random permutation is applied to the entire 4 kilobyte sector. So a change to any bit of the plaintext in that sector affects the entire ciphertext and vice versa. And for every tweak, it should appear to be a completely new permutation. Not only does this give us better security properties, it gives us an opportunity to be faster. Because we're operating in much larger bulk on the data, we can use primitives that work in bulk and give us greater speed in bulk. An SBRP has to read every byte of the plaintext before they write anything. And so you have to have at least 2 passes. Because we want it to be super pseudo-random, we need the same property in the decryption direction, which means a minimum of 3 passes. So we've gone for a hash-XOR hash structure simply because the hash is faster than the XOR. And so doubling up the hash is faster than doubling the XOR up. And we're inspired by examples like, I mean, there's a lot of interesting work in this area, which is cited in the paper. We're inspired by examples like HCounter and HCH, which, like the other work that we looked at, is based on the assumption that you're going to use AES and you're going to use multipliers in GF128. HCounter and HCH have this hash XOR hash structure. They have a narrow 16-byte block on the left, and they use that. They hash the wide block on the right to combine with the block on the left. They use that to generate the nonce that goes into the counter mode encryption, and then they hash again on the other side. And there's a single block cipher call on the thin block on the left to defeat the Luby-Rakoff attack on the 3-round Feistel structure. But because, like the other things I looked at, this is based on AES and GF2 to the 128, it doesn't perform it achieves better security properties, but it doesn't perform better on our hardware. So the work we did was simply to take these ideas in HCounter and HCH and combine them with the ideas from RFC 7539 with the high performance primitives we have. And so that means we changed the hash combiner on the left to addition mod 2 to the 128 because that's the combiner that works well with our hash. But the structure is basically very similar. We also, because Chachar is very well behaved compared to AES and counter mode, we can achieve a slight optimization where we don't have to, what's the phrase I'm looking for? We can achieve a slight optimization where Chachar and AES can run in parallel in the decryption direction, so that we sacrifice the symmetry of encryption and decryption, but it can give us an opportunity for a slight speed up in decryption. And so that gives us a massive performance boost. 17.8 cycles per byte, well over twice as fast as AES XTS. And that was a big win. But we needed it to be, if we were going to, the discussion we were going to have with OEMs trying to make sure this feature was mandatory was going to be a lot easier for every cycle per byte I could shave off this mode. So the first change we made was we switched from Chachar 20 to Chachar 12. Currently, the best attacks on Chachar break 7 rounds, and that's been the case for over a decade now, and it's seen a lot of cryptanalysis in that time. So every round of Chachar adds a lot of strength, and so we felt good about choosing that mode. That gave us 13.6 cycles per byte, which is a significant improvement. But there was room for one other improvement, which is that while Poly 1305 is very fast, there are still faster epsilon almost delta universal functions on this hardware. And so we looked at NH for hashing the bulk of the data. NH is blindingly fast, around 1.5 cycles per byte. NH's output is variable length. The more you hash, the larger its output. So we use NH essentially as a compression function to reduce the amount of data we feed to Poly 1305, and then Poly 1305 handles the final hashing stage, and that's then combined with the tweak, and that gives us our mode adiantum at 10.6 cycles per byte. And so this is the overall performance, where so because of the single AES encryption, we get faster the wider the block we're encrypting, but we're still fairly acceptable even on the 512 byte sectors that you used to get on old devices. And we're faster than, not only faster than AES, we're faster than other block ciphers such as Noekeon and Spec. And there's a larger performance table in the paper. I think I've got time to talk a little bit about the proof. It's fairly straightforward. So this is the main step in the proof, where the adversary is trying to distinguish between two worlds, world X and world Y. They can make plaintext and ciphertext queries of any length and tweak. So world X is essentially adiantum, except we replace the block cipher AES with a random permutation pi, and we replace Chachar with a random function f. In world Y, for every query the attacker makes, they get a random reply of the appropriate length. And we're going to use the H coefficient technique, which is, thanks to one of my reviewers for pointing that out, suggesting that. And so after the final query, we're going to make the attacker's life a little bit easier. We're going to give them the hash key, which can't hurt and can only help them. Once the attacker has the hash key, one thing they can do is calculate all of the intermediate hashes inside Adiantum. So you've got this diagram where you've got these hashes being either side of AES, and we're going to allow the attacker to calculate those. So they can put in the plaintext at the top, tweak at the side, and get the plaintext hash, and the same thing for the ciphertext at the other end. Having done that, they can look for collisions either in the plaintext hash or the ciphertext hash. It doesn't matter if a plaintext hash collides with the ciphertext hash, it only matters that if there's a collision in a specific layer. And if they find such a collision, they're going to win. What's the probability? For whatever queries they do, we can bound the probability of finding such a collision. And because the wonderful thing about the H coefficient technique is we only have to consider the probability in world Y. This is the effort that it saves us. So for the result, it's pretty simple. The result is totally random. So the right-hand side is totally random, and it's combined with whatever the hash value is, but the result is totally random. So the probability to collide with any specific previous query is 2 to the minus 128. This is assuming a plaintext query. It's all the exact opposite for a ciphertext query. For a plaintext query, the epsilon, we rely on the epsilon almost or universal property of the hash function. We forbid pointless queries. So given its plaintext query, either the plaintext or the tweak or both must, for any given previous query, one of those two has to be different. And so the result is the probability that the hash will differ by any given amount is at most epsilon, meaning the probability there'll be a collision in the plaintext is at most epsilon. And so across all pairs of queries, the probability that we'll see such a collision is at most epsilon plus 2 to the minus 128 times q choose 2. If that happens, we call that a bad transcript. And so supposing we get a good transcript, what's the probability, given the queries the attacker, for a given deterministic attacker, what's the probability we'll see a particular set of responses? In world Y, it's pretty simple. For a given response, the probability is 2 to the minus p. All responses are equally likely. The length of the response is the length of p, and so 2 to the minus the length of p. In world X, it's almost the same. We'll see a particular response, first of all, if f has exactly the correct output, to zoro into the content on the left-hand side to convert it to the expected content in the ciphertext. The probability of that is 2 to the minus the length of p minus 128. On the right-hand side, pi has to encrypt in just the right way. For the first query, the probability of that is 2 to the minus 128. As the queries go on, because this is a good transcript, it's always producing a value that it's never produced before, and it's always guaranteed to produce a value it's never produced before. And so its probability of getting it right goes up by a tiny bit every time. And so that's 1 over 2 to the 128 minus I, where I is the number of queries before this one. I should mention that the reason why we can say, make the assertion I did about f is because the nonce being fed to f is unique every time, and so its output is always independent from all previous outputs. And these two probabilities are also independent. So overall, the probability we'll see this, well, it's this formula here, it's the product of the two, but the important thing is this is always either the same, depending if it's one query, or just a little bit bigger than the probability in world Y. And these sum across all queries. So now we can apply the H coefficient technique. Every good transcript is at least as likely in world X, world Y. We've bounded the probability of a bad transcript, and that bound, it bounds the distinguishing advantage, which is at most epsilon plus 2 to the minus 128 times q choose 2. So epsilon depends on some bound on the length of the message and the tweak the attacker sends. We're using polynomial hashing, so the longer the message gets, the longer the tweak gets, the larger epsilon gets. But we plug that into our formula, and we add terms for PRP, PRF bound, and for char and AES. And we get this rather large expression, but the key thing is that it is linear in the message and tweak length, and it's quadratic in the number of queries, and it's small. Okay. The good news is Adiantum is already part of Linux 5.0. So I don't really think in terms of years. I don't call years 2017 and 2018. I call years things like Oreo and Pi, because those are the names of the Android dessert releases that come out in each year. So this year's release was Android Pi, and we have added Adiantum to Android Pi, and some devices will be using that. And in Android Q, which we don't know what it'll be called yet. If you know of a dessert with that's called after the letter Q, please let me know. There will be no carve-out. We will require encryption on all devices, and where AES is too slow, those devices will use Adiantum. Thank you very much.
Any questions from the audience? So then I will ask a question. I was wondering, so you said it has some favorable properties compared to XTS. So could it be also interesting to use it on the devices which have AES support and then replace the cha-cha call with AES in counter mode or something? Is that something you looked at, or?
Where you're using something like AES-C instructions, that's very appealing. A lot of these devices have inline encryption engines, and there it's harder to make changes. But also, an SPRP mode is a terrible fit for an inline encryption engine. They want to be able to stream the data past. Oops, excuse me. They want to be able to stream the data past and decrypt it as it goes. And an SPRP mode totally rules that out. You have to read everything before you get to write anything. And so maybe that's possible, but I think that will be that will take a little bit longer to land.
Okay. And maybe another question I was interested, just maybe could you give some ballpark figures, like how many % of Android devices this would be deployed in the next year?
I know it's many millions, but I think I'm not allowed to say.
Okay.
I think that sort of thing is super.
So we take this question offline?
But it's a lot. I mean, you know, it's the next billion users we're aiming this at. It's a lot of people.
Okay. Then any questions from the audience? Then let's thank the speaker again.
Let's see, this works.
Okay. So the next talk will be libintermec Beyond Confidentiality and Integrity in Practice. And this is work by Torben B. Hansen, Martin Albrecht, and Kenny Pedersen. And Torben will give the talk.
Thank you, Stephen. So I didn't quite get the honor of being the last speaker, but I guess I can unlock that and cheapen some other day. So yeah, this is joint work with Martin Albrecht and Kenny Pedersen. Just a quick outline of the next 20 minutes. Can you hear me here? I should go closer. I'm a bit tall for this. Here you go, maybe this is better. A quick outline of the next 20 minutes. So first we'll go over some motivation. And then I will introduce to you the libintermec, which is the library we built. And then I'll show how we use libintermec to implement new SSH encryption schemes. Okay. And I guess I have to start over. libintermec. I don't know what's going on. There you go. So you all probably know and use SSH. It's a very widely deployed protocol that protects a large amount of traffic. The SSH transport layer protocol, which is called the binary packet protocol, defines the packet format and the cryptographic processing you do on them. It provides the fundamental security guarantees of SSH, which is confidentiality and integrity of data. But SSH actually aims at going beyond those fundamentals. So RFC 4251, which defines the overall architecture of SSH, lists a number of other security guarantees that SSH wants to provide. And we want to focus on two of these, denial of service and traffic analysis. And we're going to consider these as properties of SSH encryption schemes. And by doing that, we can actually formally capture what it means to be secure against denial of service and traffic analysis. So the tool we want to use, that we are going to use for this is work by Boldreva, De Gabrieli, Patterson, and Stam from 2012. So they introduced the notion of symmetric encryption schemes supporting ciphertext fragmentation. So how does this work? So let's say that Alice produces a ciphertext and sends it to Bob. So the normal assumption you're making is that Bob's received this ciphertext in its entirety. Sometimes you also call this atomic delivery. But that completely neglects that when traffic or data traverses networks, there's a chance of arbitrary fragmentation. So the ciphertext C might arrive at Bob in fragments, and these, and we'll call these ciphertext fragments. And it's then up to Bob to somehow encrypt these fragments, but still arrive at the underlying message. So it's this induced fragmentation that BDPS calls ciphertext fragmentation. And that's what we're going to use to formally define these security properties. So BDPS, together with Albrecht, De Gabrieli, myself, and Patterson, defined a number of different security notions in this setting. There are the fundamental ones of confidentiality and integrity, but also two more advanced ones that is called boundary hiding and DOS. I will give you a flavor of how these works, but I'm not going to venture into the nitty-gritty details. So boundary hiding is going to capture security against traffic analysis. And it essentially says the following. So if the adversary is giving a sequence of ciphertext, then it's impossible for the adversary to delineate the ciphertext boundaries in this sequence. There are two versions of this. There's a passive version where the adversary only has access to the encryption oracle. And then there's an active version where the adversary also has access to the decryption oracle. The DOS notion is going to capture security against denial of service, and it's parameterized by a parameter lambda. And this notion is it's kind of technical, but essentially says that no adversary can make Bob hang or wait by making him expect more than lambda amount of ciphertext. So this essentially says that the lower the lambda is, the better Bob is at detecting denial of service attacks, and the faster he can respond. 2 seconds. Okay, so SSH supports a number of different encryption schemes, all listed here. And ADHP did a study where they analyzed these schemes with respect to the security notions we have just seen. And it turns out to be a pretty negative study, probably not as bad as Brexit, but close. So only Cha-Cha and Cha-Cha-Poly and Encrypt and MAC meets the boundary hiding, the passive notion for boundary hiding. However, these two schemes has other noticeable drawbacks in the context of SSH. First of all, Encrypt and MAC is not generally secure, which was both proven by Albrecht, Patterson, and Watson in 2009, but also by ADHP. And I guess we can all agree that encrypting or decrypting on unverified data is probably not very good. All right, so even though Cha-Cha-Poly is a very great scheme, it can utilize AES intrinsics, which is pretty bad in some popular context where SSH is used. So we see that none of the current SSH encryption schemes adequately provides the desired security properties. So two natural questions to ask are then, can these security properties be realized simultaneously in SSH? And at what cost? Oh, shit. Oh, no, you saw all of it. I guess kind of finished now then. All right. So to answer this question, is maybe not surprised that we're going to start out with looking at this scheme called intermag. So this scheme is pretty simple. I'm going to explain how it works. So giving a message, this message, you first split it into equal-sized chunks of length n, counting in bytes. Then this n you call the chunk length. You then encode each chunk with a byte 0, except the last chunk, which you will encode with a byte 1. You then encrypt each encoded chunk, and you compute a mag over it. But you see that to be able to prevent reordering attacks, you have to include 2 counters into the mag computation. Okay, so to arrive at the final ciphertext, you just concatenate everything together. And to decrypt, you just shift your gear into reverse, you verify the mag, you decrypt, and then you inspect the encoding byte. And if this encoding byte is the 1, you have recovered your plaintext. All right, so this scheme was also proposed by BDPS, and they proved that it achieves confidentiality, integrity, denial of service, and DOS. Right, so we want to go ahead and implement this, but before we did that, we realized that BDPS kind of cheated, because this scheme only supports messages that is a multiple of n, which is not really good in practice. Luckily, there's an easy way to resolve this. We just apply some padding. Now, the padding scheme we're going to use is pretty simple. If the last byte of the message is 0, you just pad with 1s. And if it's not 0, you just pad with 0s. So it's pretty simple. We did some other changes to the intermag scheme. We also didn't want to add padding if the message was already a multiple of n. So we encode this information in the last encoding byte of the last chunk. We also replaced this encrypt and mag construction with more modern, non-spaced authenticating encryption schemes. By doing that, we somehow need to figure out a way to include the counters to prevent reordering. We do this by generating the nonce from the counters. Oh, and then we proved that this modified intermag scheme achieves all the same security notions: confidentiality, integrity, boundary hiding, and DOS. All right, so we went ahead and implemented this, and we called the implementation libintermag. It's a C implementation, and we kind of tried to make it a fun library to use. So we have a small API, which should also make it easier to use. We completely remove the responsibility of nonce management away from the user, and handles all this internally. We also have a feature of algorithm agility with respect to the underlying non-spaced encryption scheme. And right now we have code for ASDCM and Chatapuli. And you should note that you shouldn't so I overload the naming here. You shouldn't confuse these two with the SSH encryption schemes of the same name. The SSH encryption schemes, the definition of those and the name you use of those includes more. It also includes encoding and processing of packets. Anyway. So another thing I will mention is that we try to identify attack vectors that goes beyond the formal model and implement countermeasures against them. So I'll go into a bit more detail of one of these. And it kind of shows that even though intermag has a really, really simple description, you kind of have to keep track of a lot of things when you have to implement it. So one issue we identified was with the decryption algorithm. So let's rewind a bit and go back to the boundary hiding notion. So recall that it says that the adversary cannot delineate ciphertext boundaries in a sequence of ciphertext here. But the thing the adversary can do is to measure the response time from the decryption algorithm, or Bob. And this is not captured by the formal security model. So if this response time is somehow ciphertext boundary dependent, then the adversary might be able to delineate the ciphertext boundaries. So to combat this, we have to make sure that the execution time of the decryption algorithm is independent of ciphertext boundaries. So one source of non-uniform response times can come from padding removal. So remember, you do this when you decrypt the last chunk, and you inspect the encoding byte, and if this encoding byte tells you that there's padding, then you have to remove it somehow. The first thing you have to do is to figure out how much padding there is. And the most optimal way to do this is probably just to start from the end, and then do a backtrace until you find a byte that is different, and that will reveal the the amount of padding you have. However, obviously, this takes time proportional to the amount of padding, which kind of reveals the boundaries, the ciphertext boundaries. So, I'm moving this. So we implement a constant time padding removal function, and what it does is that it searches through the whole chunk. So it visits each byte exactly once. And we also invoke this algorithm on all chunks of all messages, not to leak which chunk you're removing padding from. So obviously, doing a linear search over all chunks of all messages kind of must add some overhead. So we did a study to show how much that is. So we decrypted an 8 kilobyte message for different chunk lengths, and where we implemented a decryption algorithm with constant time padding removal and another one with non-constant time padding removal. And this simple study showed that using a constant time padding removal algorithm slows the decryption down with a factor between 4 to 5, which is kind of significant. But we wanted to make to have maximal security, so we still implemented the constant time version. Okay, so we identified additional timing channels of the same format, and we implemented countermeasures against them. However, in the code, there are still some branches that depends on ciphertext boundaries, so we cannot really claim that we have a full constant time decryption. We think there are still a lot of open problems in this area, and I guess I can use that as a shameful plug to make you read the paper if you want to know more. All right. So we also looked at how the performance is for lived intermag, and kind of did some extensive benchmarking. We did it for four different message lengths. And this shows the decryption, encryption algorithm, where we use AES-GCM as the internal non-spaced encryption scheme. The y-axis denotes the chunk length, and the x-axis denotes the performance measured in cycles per byte. And if you go through this chart, you'll see that for each message length, the optimal performance you can achieve is between 1.4 and 2.5 cycles per byte. So it's not that bad. The story completely changes for decryption. So here you have a slowdown of a factor of 10. And much of that you can trace back to this constant time padding removal. It slows even more down if you use Chachapouli, which slows it down with a factor between 25 and 35. So obviously, these measurements are done on a machine that supports AES intrinsic. So, I mean, that's why Chacha is quite a lot slower. However, we didn't think much about speed, so we still think there's a lot of there's still a lot of room for improving these measurements. Okay. So now we have a solid scheme on implementation of intermag. And we want to see how, we wanted to see how it performs in SSH. So to do that, we implemented intermag-based encryption schemes in OpenSSH. So this required us to do a number of changes to OpenSSH. So this is the SSH packet format. It contains a length field, padding length field, that measures this amount of padding and stuff. But most of these fields actually becomes redundant when you use intermag. You don't really need them to process packets anymore. So we removed them. We also implemented standalone code path for intermag encryption and decryption. This, first of all, circumvents some really bad history of some of the OpenSSH code. But we also needed that because intermag is kind of really different from some of the other encryption schemes that OpenSSH supports. And for that same reason, we had to implement some non-standard buffering of the output from the intermag decryption algorithm. So if you sum all this up, this kind of shows that if you want to integrate intermag into your application, it can become quite complex, unfortunately. All right, so we did two studies to see how well intermag performed in SSH. So the first study, we transferred 50 megabyte using SCP, and I know SCP is not really good, but that's what we had. And we want to use SCP because it's an SSH-based transfer protocol. So we did this between two EC2 instances in two different availability zones on AWS. And by doing it between two availability zones means that the distance is really short, Also, the network is extremely fast. So the first the first observation you can make is that, that the intermag encryption schemes that we implemented performs kind of on the same level as Chatterpulli, the Chatterpulli scheme in OpenSSH. And Chatterpulli is currently the default encryption scheme that OpenSSH uses. A general observation you can make is that this performance seems to be computationally dependent. This kind of changes in the second experiment we did. So here, instead of doing it between two availability zones, we did it between two different regions. So this means that the distance greatly increases, but also the network becomes kind of not so good. And it's clear to see that performance is no longer computationally dependent, but it's probably more network dependent. And it has a really great similarity with this other graph over here, which shows the ciphertext expansion for each encryption scheme in OpenSSH. So for the existing schemes, this is just some of them, there are many more, it's quite uniform. There's not much difference between the schemes. This changes completely for the intermag schemes, where we have a great variety of different ciphertext expansion amounts. And the reason for that is because of the padding, and how this padding, or how the messages fed from this SCP application down to the transport layer interacts with the chunk length from this padding, which creates this really weird distribution. But we observed the ciphertext expansion between 10 to 35% for the intermag schemes, which is quite a lot. It also creates this funny thing there. Anyway, to conclude, so the answer to the first question is yes. We implemented intermag. We also tried to identify issues that goes beyond the formal security model. And we think that our intermag-based encryption schemes in OpenSSH kind of captures the desired security that SSH wants to provide a bit better than the existing ones. But using intermag also adds some cost or overhead. So we observed increased complexity in integration and implementation. This affects performance to some extent, but depending on your use case, this might or might not be tolerable. You can find our code on GitHub, or you can hit us up on Twitter. Thank you.
Questions?
Don't you think that having these new libraries couldn't also be a good opportunity to implement some of the CISA algorithms? And do you have plans for that?
That would be a no.
No to which question? A plan, or isn't it a good opportunity? None of them.
Yeah, maybe. I mean, everyone can implement it. It's pretty easy to implement new schemes for. Let me go back. Let's go all the way back. There you go. It's pretty easy to do this in libintermag. So I made it easy for other users to actually implement schemes. You just have to program against an interface, and then you can quickly use it. So, I mean, anyone is invited.
Thanks.
If there are no further questions, then thank the speaker again. So now to the last talk of FSE 2019, which is towards low-energy stream ciphers by Subhadeep Panik, Vasily Mikalev, Frederick Armknecht, Takanori Sobe, Willy Meyer, Andrei Bogdanov, Juhai Watanabe, and Francesco Regazzoni. And Vasily will present.
Thanks a lot, Stefan, for the introduction. So can you hear me well? Perfect. Yeah, this is the work done by many authors, as you can see. So I'm going to talk about energy efficiency in stream ciphers. So a short outline of my work, of our work. So I will start with introduction. So in principle, I will explain why we are doing this, give some motivation, explain the current state of the art. Then we will go to the comparison of the stream ciphers with block ciphers to figure out in which scenarios, which ones are more efficient energy-wise. And then we will discuss the energy impact of individual components of stream ciphers and of different design decisions. So in principle here our goal was to figure out how do we design the stream ciphers as energy efficient as possible. And I will come up to the conclusion then. So, although these two terms are really related, energy and power, they're in fact different. So, people often confuse them. In fact, energy is the time integral of power. So, energy is linked to the total electrical work done by the device. So, I mean, we can consider it probably as the most fair metrics to analyze the lightweightness of this or that design. So in the applications where energy is crucial are the battery-operated devices, body implants, different IoT devices. So when we talk about designing a cryptographic primitive, there is usually a trade-off between speed, costs, like resources, amount of resources, and the security. So the security is something what is fixed, so we cannot do anything about it. But usually the goals are either to increase the throughput or to reduce the resources. So if we want just to increase the speed, I mean, if we don't care about anything else and our ultimate goal is just the throughput, I mean, that's fairly easy. So we just use more resources for that. So for example, I mean, we can parallelize everything, we can just copy the primitives and implement them twice, whatever. In the case when our goal is just to reduce the area and the power, which is closely related to area, it's also quite simple. So in principle, we do our design in such a way that we use minimal logic and minimal area and whatever, but we don't care about the speed. So we do it really many times with very simple, let's say, Boolean functions, and after enough number of updates, our state is already well confused and all the initial bits are distributed very well. So this is another way to go. But when we actually want to optimize energy, this is not so simple, because here we have to consider both. So we want to increase the throughput and or decrease the power consumption. So in principle, the main idea while optimizing the energy would be to increase the throughput by a larger factor than you increase the power, or the other way around. So reduce the power consumption by a larger factor than the throughput. So what do we have so far? This area of lightweight cryptography, I don't know how old it is, maybe 15, 20 years already, but by now or by recently, most of the focus have been put on the designs for low area and, I mean, quite many designs for low power, but there was not much about low energy consumption until the work of 2015 of Barnick and the others, where at SEC they carefully investigated the energy consumption of block ciphers. And following this research, the block cipher Midori, which was specifically designed for energy consumption, was developed. However, the energy efficiency of stream ciphers was never investigated in a good manner. So this is actually our goal here, to investigate different design components and to see how stream ciphers perform energy-wise. So what we start with is the comparison of stream ciphers with block ciphers in order to see if it makes sense at all. Because, I mean, if, let's say, energy of stream ciphers is much worse than block ciphers, maybe it does not make sense to consider it. And actually, there is a common belief when people think that because of the long initialization phase of stream ciphers, they only make sense when we want to encrypt really huge amounts of data. But for the short amounts of data, which is usually the case of the lightweight crypto, I mean, stream ciphers are much worse as compared to the block ciphers. So we wanted to figure out if this is true. And I mean, in this work, we analyzed the following ciphers. So for the stream ciphers, we took the two eStream finalists, Grain and Trivium. So these two have two different conceptions behind their design. So Grain was developed to have the minimum internal state size. So its internal state size is just twice the key size, which is given by the time memory data trade-off attack. While the Trivium was designed to have as small update and output functions as possible. So they did not care too much about the internal state size, which is much bigger than this trade-off. However, they managed to use really, really simple functions. So we also took a look at Trivium, which is a tweak of Trivium, but for 128-bit security. So just some small changes were included into it in order to get rid of the attack of the normal Trivium if 128-bit was used. And we also looked at two recent examples of stream ciphers. These are Plantlet and Lizard. So some tricks there were used in order to decrease the internal state size below this trade-off curve. So in principle, they use short internal state size, but they actually have to access the key more often. And regarding block ciphers, we considered present, which is a standard, which was standardized, and it was also shown to be very extremely efficient for energy consumption. And of course, the Midori, which was specifically designed for it. So if we take a look at the best cipher configurations with respect to the energy consumption, I mean, I will later explain what the best cipher configurations are when I will talk about the design decisions and so on. So we can see that Trivium is actually much more energy efficient than the best Midori implementation. But this is when we actually want to encrypt 1,000 blocks, and one block is 64 bits. So this is nothing really surprising. This is what we more or less expected. But let's also see what happens when we look at the small rounds. So at this graph, you can see energy consumption for the different number of blocks to be encrypted by different ciphers. And what we can actually see here that the Midori it actually provides the best energy consumption, the lowest energy consumption when we want to encrypt just one block, just 64 bits. However, when we want to encrypt 2 blocks of data, Midori already is worse than, for example, Grain version 1 and Grain 128. And after 6 blocks of data, Trivium outperforms all other candidates. So we actually focused our research on these two ciphers, Grain and Trivium. So now we're going to discuss, the insights, what leads to this behavior. And the best thing, or the most efficient thing, what you can do in order to optimize the energy consumption of stream ciphers is to unroll rounds. So in fact, the idea is to increase the throughput again at the cost of the area. But this is not just doubling everything. So the idea is that we only replace the logic designed for one round by the one which implements several rounds, as you can see here. However, we keep the same register. So there is no need to copy the registers in order to double or triple the throughput or whatever, but just to copy the logic. And the stream ciphers were especially designed to allow this to be easily done. So in fact, most of the stream ciphers used feedback shift registers, and if the last bits of each of the feedback shift register is not used neither in the update nor output function, we can simply copy these functions, and then instead of shifting the values in the state by one position at every clock cycle, we can shift by 2. This allows us to double the throughput by the cost of just copying the functions. So the same strategy of development was done in Trivium, for example. So in fact, many stream ciphers were designed to allow this easy unrolling. So in case of Trivium 1, the 16 bits are neither used, the 16 last bits are neither used nor in the output nor in the feedback functions. So this allows to easily unroll 16 rounds. So this is the 16 bits per clock cycle version of Grain version 1. However, further unrolling is also possible, but it requires more complicated algebraic structure of the update functions, because simply adding more copies of the round functions will not lead to the correct functionality anymore. So after we start increasing the throughput by unrolling further rounds, we still get the improvements of the energy, but this happens only until a certain point in time, and beyond a certain degree of unrolling, the increasing actually results into increase of the energy consumption. So there is sort of a parabolic behavior. So if you take a look on the table, for example, we can see that up to 20 rounds, the power consumption or the energy consumption, not the power, the energy consumption goes down. But after this, it goes up again. And in case of Trivium, this number of rounds is 160. So up to 160 rounds of unrolling, we get the decrease in the energy consumption per block, and afterwards it's being increased. So in order to figure out what's actually happening internally, we took a look on the power shares of Grain and Trivium for different degrees of unrolling. So recall that the update function of Grain is much more complicated than the update functions of Trivium, but it uses less internal size and actually less number of clock cycles in the initialization phase. So for 1 degree of unrolling, so the classical implementation, we can see that the logic of Grain takes extremely low part of the entire energy. But as soon as we start increasing, it's actually taking most of the energy. Already after 32 degrees of unrolling, we have around 64% of energy taken by the logics, and for 64, it's almost everything which is taken by logic. So if you can see, for example, here we increase the throughput twice, so 32 versus 64, but the power consumption taken by logic increases more than 4 times. But in case of trivium, this does not happen so fast. So in the beginning, again, the logic takes just a small portion of the entire energy. But even in the case of the trivium 160, so when we unroll 160 rounds, we only take around 1/2 of the entire energy, and the other half is taken by the register. So the lesson that we can learn from here is that in order to really optimize the energy, just design a cipher which has very small functions and don't care too much about the state. So this is the major thing that you can do, but we also decided to look at the more small design decisions which could also help us to improve the power consumption. So the first one was to consider different types of flip-flops. So in fact, the stream ciphers registers normally have 2 inputs. So in the beginning, they have to be initialized with the key on the IV. And during the clocking process or the initialization phase or the key stream generation phase, the registers are being updated, so by some functions. Therefore, we have to have 2 inputs, and therefore we need a multiplexer to figure out which input goes into the register. So there are 2 ways of realizing it, either taking a simple flip-flop with a multiplexer before, or we can have a scan flip-flop which already provides this functionality. So this is the result, and we can see that for all cases, the scan flip-flops outperform the regular ones. So when you're interested in the energy consumption, use scan flip-flops. Another thing is the architecture. So the feedback shift registers can be realized in Galois and Fibonacci configuration. So in fact, this is based on either we have just one update function in one register, or we just split the update function into smaller ones and to feed them into different registers. So in fact, there is no big difference, but the Fibonacci ones were a bit better, and they actually also allow us to easier unroll. So it's better to use Fibonacci ones. And another parameter that we looked at is how do we actually implement the round function. So there are different ways. The lookup table, we can just give the functionality to the synthesizer and ask it to optimize. And using the decoder switch encoder configuration, which in principle was shown to be optimal, for example, for implementation of the RAS boxes. So in case of the stream ciphers, the most efficient was always to give it to the synthesizer to optimize it. So just to summarize the lessons that we've learned, so it's better to use scan flip-flops in the Fibonacci configuration, let the synthesizer to optimize everything. And the really key way to optimize energy consumption is to use simple update functions. So the state size is less important, and in principle, the initialization time can also be large, but after a certain time, or after the certain degree of unrolling, it becomes less important. So we looked at different parameters, and we can summarize that for longer data stream, multiple rounds unrolled stream ciphers perform better than the block ciphers. So even for 2 blocks of, if you want to encrypt as much as, let's say, 128 bits, the energy consumption will be less if we use certain stream ciphers rather than the best block ciphers. And the key to it is the simple functions. So the further steps would be to come up with the even more energy efficient designs. So we tried to beat Trivium, and it appeared to be not so far. So it seems that the design was really good in terms of the energy consumption. But for example, the designs, Trivium allows only for 128-bit security, or for 80-bit security. But if we want to go for 128-bit security, it seems that we can beat Trivium, at least slightly. So in principle, another possible further step could be just to fix some parameter and try to optimize energy under these restrictions. So for example, if we limit the area size, I don't know, to 2,000 gate equivalents, let's say, which is a common threshold for lightweight devices, we can optimize the energy consumption there. Or we say that we have limited power consumption just supported by the device. What will happen then? Or if we need to have some fixed throughput, we can also take a look what would be then the best way to optimize the energy. So thank you very much.
Any questions? And I have a question actually. So could you maybe give some insight how you arrived at these energy numbers? Like what is the target platform architecture? Or is there a difference between what architecture you aim for regarding the energy consumption?
So in principle, we were working with 19 nanometers logical process. And I think the frequency was set to 10 megahertz, just because when we go for the low frequency, the role of the static power becomes quite high. So we actually wanted to see how it deals with the dynamic power. And when we talk about 100 megahertz or high frequencies, the static power almost doesn't play any role. So does it answer your question? So it's ASICs, 90 nanometers.
Okay.
Yeah.
Any other questions? Yeah, if not, then we can close the session, and thanks to Vasily again.
Thank you.
And Jeremy will announce something.
So I haven't prepared anything, but I just wanted to thank you everyone for coming. I hope you enjoyed the conference and Paris more generally. I still have a few metro tickets, if I can give them to you if you plan to visit Paris today or in the coming days. I have about 40.